and I'm very glad to have this opportunity to share some of my experience working in data analytics and share some of the problems that we encounter in real-world work. So I'm going to share a few use cases in financial services and how data science and machine learning comes in handy to solve these problems. The first use case I'm going to share is about credit loss forecast with random forest and logistic regression. And then I will talk about an economic scenario generator that we developed. And finally, I will share a use case for using neural networks to predict financial asset prices. First, let me give some background about credit loss forecast. So starting from the last financial crisis in 2008, the Federal Reserve started to enforce a very strict and rigorous risk forecast procedures called comprehensive capital assessment plan. And most of the big banks in the United States are subject to this regulation called CCAR. And in this kind of process, the banks are required to make forecasts for their, say, how much likely a customer is going to default on their loan, and how much of this loss can be recovered if the customer does default. And they want to test this kind of forecast in different scenarios. They are especially interested in the very stressed financial scenario when the GDP goes down, when S&P 500 drops, to see if the financial institutions are able to maintain a capital ratio to stay solvent. And here, this use case I'm going to share is about how to forecast the likelihood of default. Well, if you have some experience with statistics or machine learning, then you can easily understand that this can be solved as a classification problem. Either the loan is defaulted or not. And we have a bunch of explanatory variables like how much the loan amount is, and how many years this, what is the term of this loan, and also some of the characteristics of the customer. For example, what is the FICO score, and what is his debt to income ratio. These factors are taken as input, and then we usually would use a logistic regression model to make the forecast of the likelihood of default. So, as you know, logistic regression, it has advantages as being easy to interpret and transparent. But at the same time, it has some drawbacks. For example, it can only deal with linear relationship. But in many real-world problems, the relationship between our explanatory variable and the likelihood of default is not linear. In fact, sometimes it has different explanatory variables. They have interactions with each other. On the other hand, there are other machine learning models like random forest, gradient boosting, or support vector machine. They are very good at handling nonlinear relationships and interactions. However, these type of black box models, they are hard to interpret, especially when it comes to explaining which factor or which explanatory variable have the most impact on your target variable. This becomes difficult. So in this use case, I will share some methods that can help us enhance the interpretation of these black box model. and it can help us to better use them in the real case scenario. So here is a very brief workflow of the model structure. Well, we start with some variable importance. As you know, we can get that from random forest, and we also incorporate the business judgment from the financial institutions, and also from economic theory and business intuition. And then we select an initial set of variables to tune it and get the final random forest model. And then we will utilize some of the characteristics or facts we observe from random forest model to improve our feature engineering in the logistic regression. The key tool we are using here is, first of all, the feature importance. Feature importance in random forest is yearly calculated by accounting for how often a feature appears as a split node and how steep this split node appears. And another tool we use here is called a partial dependence plot. This kind of plot is designed to visualize the relationship between a feature and the target outcome after controlling the effect of other explanatory variables. This kind of plot allows further examination for the consistency with economic and business intuition. For example, in economic theory, we often observe that when GDP growth rate drops, then an unemployment rate increase would follow. If your model detects otherwise, then it's more likely that your model is wrong. So we want to check in our model to see if the relationship displayed in the model is consistent with economic theory. Here on the right-hand side, we have the partial dependence plot of Japanese GDP growth rate. Remember that our dependent variable is the likelihood of default. So it is more likely that when Japanese GDP growth rate drops, our likelihood of default is going to increase. So there would be a negative association between these two variables. However, in the plot here, we observe an upward trend after a certain point of the Japanese GDP growth rate. To keep the model more consistent with the economic theory, we would then cap the Japanese GDP growth rate at 0, so that the trend we observe is consistent. At the same time, partial dependence plot also allows us to observe different interactions between different variables. On the on the left-hand side, we have the partial dependence plot for U.S. real GDP growth grouped by project finance flag. Project finance flag is just labeling whether this loan product is for financing a certain kind of project. And we can see that the different loan types, whether with or without project finance flag, the likelihood of default responds differently to the real GDP growth rate. So this can further help us interpret the model. However, there is still one problem with random forest, is that it is very difficult to quantify the marginal effect of each feature. So we utilize the partial dependence plot from random forest as well as the feature importance to guide us engineer additional features in logistic regression. For example, from the plot we just see, we can include an interaction term between project finance and real GDP growth rate. Also, we may want to include a certain kind of nonlinear term for Japanese GDP growth rate. Additionally, we would also visualize the features with the target outcome to see how the target outcome responds to different values of our feature. And finally, we will perform statistical tests to see whether these features included are significant and whether they are able to improve the model performance. And shown here are the results for the likelihood of default forecast over a historical period of time and also under different economic scenarios. The red line represents severely stressed economic scenario. The orange line in the middle is adverse scenario, and the blue line is just a baseline scenario. And we can see that both models have good performance, as that they are able to fit the historical data pretty well. And we also observed that the random forest model is able to give higher in-sample AUC, which is a commonly used metric to assess whether a model is good or not. And at the same time, we cannot deny that the logistic regression models, although it does not have as much higher AUC as random forest, it does provide more transparency about how your target outcome reacts to different input features. And this kind of characteristics are highly desirable in capital planning and risk management process. And the second case I would like to share is an economic scenario generator that we developed. So simply speaking, the economic scenario generator aims at simulating the realistic joint distribution of time series paths for a large number of input economic variables. Although that this is originally designed for economic forecast, but this same framework and same concept can be easily applied to different areas. Here, in order to generate good economic scenarios, we need several features here. First, this generator should be able to include a large number of variables. It should be able to include, say, 100, 200, or even more. And secondly, we need to preserve the time series dynamics of the individual variables. And at the same time, we need to account for the interdependence among different variables. For example, if we include interest rates of different terms, then we would like to keep that the longer term interest rate is higher than the shorter term interest rate. Sometimes if we don't take care of this, the model would predict otherwise. Also, we want to capture the asymmetry and excess kurtosis of the distribution for many economic and financial variables. For example, for the stock market variables like S&P 500 or the volatility index VIX, these kind of variables often display asymmetrical characteristics. Say if it would be more severe towards the adverse scenario. We would also like the this design to be able to incorporate different expert judgment, as well as the scalability to expand the variable universe without building complex models. And the key steps we built this economic scenario generator is that we want to capture the interdependence among different variables. So we utilize the principal component analysis to decrease the dimensions of the variable universe. And then we capture the interdependent dynamics of these variables by modeling these factors with an augmented bar process. Then from this augmented bar model, we would map the factors back to the individual factors and then make the forecast. The generated outcomes are, say, thousands or tens of thousands of simulated forecasted paths for each individual variable. Here's an example of the input variables. We incorporate general economic, interest rates, equity markets, real estate and commodity, as well as the volatility measures. Here's some of the sample output for the key variables. Showing on the top are the US real GDP growth rate, as well as the VIX. And on the bottom, we have 10-year Treasury yield and the Dow Jones stock market return. In the next few pages, I would like to share how this scenario generator can be used for different institutions. One of the use cases that we want to adapt this economic scenario generator to a specific financial institution. So each financial institution, they have their own risk appetite, and so that they would have their own expectation for the future. So this use case actually calibrates the institution-defined baseline scenario to our economic scenario generator, and that generates the forecasted distribution. In other words, the generated forecast distribution is baselined on how this institution thinks the future is going to be. It's more specific to their own risk portfolio. And showing here are some is an example of how we calibrated this baseline scenario into this ESG. Essentially, we incorporated this baseline scenario as a starting point of our simulation. However, because our economic scenario generator, it involves some nonlinear transformation in the middle, so a direct calibration cannot guarantee that the resulted simulated distribution is centered at the institution-defined baseline. So we included a correction curve. And also, this ESG can be used to quantify the likelihood of a specific scenario. Since there are potentially millions of possible scenarios, it is essentially impossible to say the exact likelihood for one specific scenario. So here we take a slightly different approach. We are trying to find from the economic, distribution that the scenarios are the scenarios that are most similar to the defined ones. In this example, we're trying to quantify the likelihood for severely adverse scenario defined by Federal Reserve, as well as an adverse scenario and a baseline scenario. And the plot on the plot here showing the bucket of each scenario. Basically, each bucket represents the scenarios that are most similar to the ones we're interested in. And then by counting the ratio for each bucket, we're able to quantify, say, how much likely this baseline scenario is going to happen. Or in other words, how representative these three scenarios are. So these are just the two of the use cases for an economic scenario generator. Essentially, you can use the output of the ESG to make forecast of your revenue. You can get a distribution of revenue forecast. Then you can be better, and then you can benefit from being able to quantify how much confident you are about your revenue forecast. So we don't have a lot of time, but in the next several minutes, I would like to share our experience of using neural network to forecast commodity price. So here, the commodity price we're forecasting is the Western Texas Intermediate price. And we are taking in inputs from different sources, for example, from the economic, macroeconomic, and the market, as well as the social media. The social media data, we are focused on extracting the sentiment toward this commodity we're interested in. We also explored several architectures in neural network, and it turns out the LSTM architecture is the most suitable case for this kind of data, because we would like to capture the time dependence in the data. And as you know, the LSTM architecture is one of the recurrent neural network, and it is developed for data with zero dependence. And compared to traditional machine learning methods like random forest support vector machine, LSTM model can be a little bit challenging because we might be facing a non-convex loss function, and it also requires tuning a lot of parameters. In our experience, we tried to tune the hyperparameters for the neural network structure, like number of layers, number of nodes in each layer, and also how many epochs we want to train this neural network, as well as the dropout ratio in each layer. And in this case, because our data only ranges from goes back to 27 months, and it's daily data, so we do not have a large volume of data. And as a result, the neural network can be easily overfitted. So detecting the early stopping in this case is really important. What we did is to look at the loss function epoch over epoch, and as soon as we see that there is a upward trending of the loss function on the validation set, we call it a stop. And here's the forecasted results. On the right-hand side is the forecast results for the WTI return, and on the right-hand side is on the price level. We also tested our model by using P&L simulations. So here we used a very simple and naive strategy. Say when the model forecasts that the WTI return is positive, then we make a long position. If it's forecasts negative, then we make a short position. And we only hold the position for 1 day. And we can see here as a result, over a period of 3 months, our model is able to generate a positive cumulative return. And here I would also like to share some of our observations for this kind of practice. Even though that in this use case we only have a small amount of data, but in this area, the data amount can potentially be very large. This kind of framework can be easily adapted to, say, intraday trading, where we have intraday data that's at a frequency of 1 minute or even, say, 5 seconds. That would be able to give us a much larger amount of data to train a better neural network. Okay, that's all. Thank you. If you guys have any questions, I can answer them now, or you can talk to me later. Yeah, please.
Yeah, when you try to fit the model, what's the criteria you said, oh, it's good enough?
So the question is about how do we tell whether a model is good enough. So for example, for the commodity forecast use case, we are trying to establish some kind of baseline scenario. For example, when we can consider it at the trading strategy stage. We can consider the model informed. We can compare the model informed strategy to a model agnostic strategy. For example, we can compare it to a random guess strategy, or we can compare it to a strategy that is based on certain kind of trend signals like MACD. And in our case, the model-informed strategy does perform better than the others.
Thank you so much,
Thank you.
Clara.